Okay, the base of any exponential function can be any positive number except for 1. Now there is one base which occurs a lot more frequently in mathematics, calculus and higher mathematics than any other exponential base. This base is defined as the irrational value e, just an italicized lowercase e to denote it as a symbol. E has a value. E is approximately 2.718281828, and even these few digits after the decimal suggest that the digits repeat. However, if you continue past these few digits, you'll see that there is no repetition to e's decimal values, which means it's a irrational number. Now again, it's an exponential base. Its values, between 2 and 3, so it has the same properties as the other exponential functions. It has asymptotic behavior on the left, y-intercept at 0, 1, steep growth on the right. And so base e behaves like every other exponential base, and you've got e located in 2 different places on your calculator. There is one use of e, probably the most common one you're going to use, is the second function up above the natural log key, the button that says ln on it. There's a little e caret x, or e raised to the x right there. So whenever you're needing to do calculations with e, let me go back to my home screen and clear it out. When you pull up that second natural log, second ln, then it pulls up e on your screen. And so if you want to check e's value like this, you just raise e to the first power, and it gives you the 2.7-ish value that approximates e. If you need to do any other powers of e, just e raised to the positive 5, for example, then that gives you the 148.4, approximation of whatever e to the 5th is. So since e is most frequently used as an exponential base, then the Texas Instruments programmers decided to go ahead and make it a default exponential expression, so that whenever you pull this up, it automatically gives you a space in the exponent to start typing whatever your exponent value is. Okay, and so when you're graphing and you want to graph the function e to the x, pull up the e, put an x in the exponent, and then assume 4 will produce a graph that looks, well, similar to the one I've got here. Asymptotic behavior on the left, crosses the y-axis at 1, steep growth on the right, indicative of all the exponential functions graphs. It's just a particular value that occurs a lot more frequently than others. Now, as a pre-calculus student, I can't really give you too much derivation as to where e actually comes from. In your first semester of calculus, you'll learn a tool called the limit that actually justifies why e turns out to be the perfect exponential base. So you'll have to cross that bridge when you get to it. But here and now, as a pre-calc student, just realize that e is just a base for an exponential function that behaves just like all the others. So if we're going to use this as our basic graph of e to the x, then we can still apply transformations to sketch other versions or transformations of the e to the x function. So if I want to sketch the graph of y equals e to the x plus 2, so as a reminder there, that's the same thing as f of x plus 2 inside the function, since the x plus 2 is in the exponent, and that's where the inside of an exponential function lies, then that means you're going to take the original shape of e to the x and shift it 2 units left. So that means we'll take a shape that looks like this, and probably the most important point to move is the y-intercept. And notice now it will no longer be a y-intercept when you move it 2 units left. So if the original y-intercept is here, is located here, and you go 2 clicks to the left, that's where that point will get transformed to. And notice it still plays the same role. Points to the left, or the graph to the left of this y-intercept, or this previous y-intercept, gets close to the asymptote. So here's your asymptotic behavior on the left side, and then the steep growth occurs on the right. But again, it does eventually cross the y-axis, probably a lot higher than what this is scaled, but that's a rough idea of what that function would look like, shifting it 2 clicks to the left like that. So your domain for any exponential function, whether it has a rational or an irrational base, will always be all real numbers. The range, we didn't shift this one vertically, so the asymptote is still the baseline for the range, meaning you go from 0 to infinity. And again, your your asymptote is still at the x-axis, so y equals 0 is the equation for this asymptote. Okay. Two transformations on this one. So we'll take the basic shape of y equals e to the x, and this one requires a negative in front, so that negative in front reflects about the x-axis. The negative in the exponent reflects about the y-axis, and then the plus 1 shifts it up by 1. So our original graph, if we do these one at a time, the original exponential graph looks something like this. Okay. I'm just going to dot that in because I'm using that as a reference. If I do these two reflections, and again, it doesn't matter which way you do the reflections because you'll still end up with the same result either way. You can reflect in the x-axis first. So let me code that one in red. That is an x-axis reflect. X-axis reflect. So if I do that transformation on the dotted black graph, that will produce a graph that looks like this. Okay, and then I want to do this transformation, which will reflect our graph in the y-axis. So you want to do these in tandem as you go. We've done the x-axis reflection, now we're going to do the y-axis reflection. So that'll be in green. If I take this red graph and reflect it about the y-axis, you keep this same y-intercept, but the asymptotic behavior is now going to be over here, and the steep part is going to be right here. Okay, and then our final transformation is to take, after the reflections are done, take the green graph and move it up by 1. So notice through all these transformations, we've still kept the asymptote at the same location. The asymptote has still been on the x-axis. So finally, for the final graph, I'm going to move this graph up by 1, and that'll shift its asymptote, most importantly. So notice your old y-intercept here on the original graph now becomes a place where you can graph the asymptote's reference line. Y equals 1 will be my asymptote equation. Okay, and then again we're shifting the green graph up by 1, so this y-intercept is currently at -1. When that gets shifted up, the graph will actually cross through the origin, and then you can mimic the rest of the shape of the green graph. It gets closer to the asymptote this way, and then the steep part continues on to the left like that. So of all these graphs here, the solid one is the final answer, the final result. And again, by all means, double check your answer on the calculator to make sure I've translated these transformations correctly. So this is the equation y equals -e to the -x, and then a +1 afterwards. So this will graph in blue, and it should look the same as the black graph I've got on the paper here. I'll do it in zoom decimal, number 4. So the steep part should be on the lower left, crosses through the origin, and then you can see it gets asymptotically close to the value y equals 1 as it continues to the right of its domain. So I got my graph correct. Domain is still going to be all real numbers. And the range is now unique because of the reflection and getting shifted up by 1. The range of y values goes from -infinity up to, but not including, 1. Okay, so the exponential function e to the x, it pops up more frequently than others in your future math classes, but here and now just think of base e as just a regular exponential base. It has a designated value, and it behaves just the same as all other exponential functions.